So far we focused mostly on the advective term of our partial differential equations and how to stabilize that term. We also looked at the limiting case where we needed the inf subconditions, and we found that we needed special spaces for our test and trial functions to make sure that we get stable discretizations. So now it's time to kind of move to our second big problem in the Navier-Stokes equation, and that was that it was of this mixed nature, and the prototypical equation that we discussed in this direction was the Stokes equation. So in the next couple of videos, the videos in this series number 7, we're going to try and motivate mixed formulations from various perspectives and try to understand their physical meaning, as well as how to treat these with numerical methods. So what is specifically a mixed method? Well, I have a book here that is called Mixed and Hybrid Finite Element Methods. So I hope to find a clean definition of what a mixed method was in that book. Now, alas, that happened to not be quite so straightforward. So we kind of have to piece the puzzle pieces together to come up with a good definition of what a mixed formulation is. And if I look through the literature now, I find a couple of similarities between the different mixed methods that they talk about. And well, typically if we talk about mixed method, then it means that we're talking about a weak formulation of a partial differential equation. And not just any weak formulation of a PDE, but we typically have multiple solution fields. Right, so for Stokes, again, as a typical example, there will be the velocity field and the pressure field. But if I'm being very formal, then I could also say, well, linear elasticity also have multiple solution fields. We have a displacement in x and y and in z. And still linear elasticity in its standard formulation is not something that we call a mixed formulation. So there has to be something special here. And I think that the key thing here is that these different solution fields live in different function spaces. So we also are dealing with different function spaces. And I think that these three points together pretty well summarize what mixed formulations are about. And we've seen that that's actually quite challenging. If we have multiple solution fields in different function spaces, then if we want to treat these with a finite element method, then we have to be very careful in our choices of these approximation spaces for these different solutions. And if we don't do this properly, then we can get all kinds of oscillations and instabilities. Now, before we go into that part of the story, the mathematical analysis and the numerical methods, I first want to really talk about the physics behind these mixed methods. So where do they originate from? And also there, I think there's a couple of different ways that we can describe these problems. Well, first we can obtain these problems, these mixed formulations, from a reduced order form of a partial differential equation. So what do I mean by that? Well, let's take as an example our classical Poisson equation. So minus this delta operator of phi is equal, let's just make it 0. So that's a second order operator. And a reduced order form means that we would rewrite that as one equation saying that the gradient of phi is equal to, and then we introduce an auxiliary variable. So say for instance sigma, and well, the gradient of a scalar is a vector, so sigma is a vector right now, or minus maybe, minus the gradient. And then the second equation would be that the divergence of sigma is equal to 0. Right, and that's now exactly the same partial differential equation as the one on the top. So these are equivalent statements. But this is a second order operator. And these are all first order operators. There's only one derivative. So what we've seen is, of what we see with this example, is that we can introduce a new variable to reduce the order of our differential operator. So why might we want to do that? Well, again, looking forward to finite element methods, we're typically kind of constrained to the smoothness of our approximation spaces. We have these piecewise linear functions, for instance. So these are functions in C0. They're continuous, but only first order continuous or zeroth order continuous, depending on how you count. So we can only take a single derivative to still be a function in L2. And so it's a subspace of H1 essentially. And making functions that are function spaces that are higher order smooth is typically quite challenging, especially in complex geometries. So if we find partial differential equations that have very high order of derivatives, and examples are, for instance, the equations that originate from shell deflections or beam deflections or phase field models, and we typically have fourth order differential operators. If we then obtain a weak form that still has second derivatives, then we can't really use standard finite elements because we're not allowed to take second derivatives of finite element functions. At least not in the typical space of Lagrange basis functions. And so this might be a technique that you might want to use to rewrite the partial differential equation a little bit, such that now we have what? We have more variables, right? Originally we only had phi, but now we have phi and sigma. But the benefit is that the order of our differential operator is lower, right? So again, looking at the example of plate bending or beam bending, you might want to rewrite it into a system of equations where each one of the equations is second order. And second order we are allowed to treat with a finite element method because you do integration by parts and then you only take one derivative when you test and one derivative when you trial functions. Okay, so that's one example of how we obtain a mixed method and why we might want that. Another example is if we have multiphysics. Problems, or in general complex physics problems. So an example there might be that we try to solve for a temperature field and a displacement field at the same time. Maybe the temperature field affects the constitutive law, so that we have to solve both of these in parallel. They're definitely different variables and they might also live in different function spaces. So that would also produce mixed formulations. And complex physics, maybe you can think of the example that I showed in one of the previous videos where we're trying to do this friction stir computation, where I'm also solving for the velocity field and the stress field at the same time. And the last key point that I want to address and one that I'll focus on for a while longer is if we have a constraint, so a weak enforcement of constraints. And specifically the example that we will look at first is if we have constrained minimization problems. So in these cases, if we have constraint minimization problems, I don't know to what extent you're familiar with your partial differential equation theory, but you would obtain Lagrange multipliers. And maybe if you've taken a contact mechanics course, then they also talk about Lagrange multipliers. So Lagrange multipliers are additional variables that somehow come into play when we try to enforce a certain constraint on our space, on our functions, on our solution, our finite element solution, or in a more general case, just the true solution to a partial differential equation. And if we try to enforce that constraint not strongly, and strongly would mean to set the condition directly on the function space, but rather we don't want to do that, but rather we would want to do that weakly. And if we do that weakly, then we introduce a new set of equations that try to enforce the constraint. A new set of equations also means that we have a new variable. And so these are three reasons why we might have to deal with mixed formulations. And I think that the The Stokes equation falls most naturally in the last one, that we have certain constraint that we want to enforce. And then actually what we'll see is that the pressure sort of originates as a Lagrange multiplier for a certain constraint. Yeah? So now this is now a video of 10 minutes. I think that I'll keep it with it, keep it at this to keep things a little bit separated. So this would then just be the introduction as to why we're going to move towards mixed formulations now. Yeah? And I guess what I also still want to say is that that in the next few videos I'll try to focus mostly on the mathematical description of the physics. If you recall in my introductory lecture, I tried to emphasize that throughout this course what I'll try to do is highlight the various aspects of the theory that we're talking about, in the sense that I think that the physics, the mathematics, and the numerics, they really aren't different, not fundamentally different corners of the story, but rather we have a combination of all these facets. So in the example of the stabilized methods, I try to motivate them from the perspective of an artificial diffusion, and diffusion is a physical phenomena. But then at the same time we try to have this diffusion to be small enough that it's a subgrid scale diffusion, that it doesn't spoil our numerical results, right? So that would be more of a numerical argument. And at the same time we also said, well, the problem that we're trying to solve is that we have this vanishing coercivity constant, and well, that's a mathematical concept. So I feel like all these things are very tightly related, and to appreciate the theory you kind of have to appreciate precisely that the physics, the mathematics, and the numerics really form different sides of the same coin. So in the next few lectures I'll try to address a little bit more the physics to also help you appreciate that perspective on the problems that we're trying to solve here. Yeah? Okay, so that's what I'll do. Stop here for this video. And in the next video, I'll talk a little bit more about this weak reinforcement of constraints, because that's how I'll motivate the Stokes problem.